Okay, so now we're going to talk about the disk method to find solids of revolution. So let's talk about the solid that we get by rotating a plane about an axis. When you do that, we call that a solid of revolution. So we're going to find the volume of a solid, of such solid, we need only to realize that the cross-section area, which we'll call A of x, is the area of a disk of radius r of x, where r of x represents the distance of the region's boundary from the axis of revolution. The area A of x actually becomes, so the area actually becomes pi r squared, because the cross sections are actually going to be circular regions in this case, and the area of a circle is pi times the radius squared. And so then that's going to yield, so if that's the area, then that's going to yield the volume is going to just be the integral from A to B, where A is, one endpoint, B is the other endpoint of the region, pi times that radius squared dx. Okay, so let me just give you an example here. Suppose we take a horizontal line. So let's say right here, see the line right there? That's the horizontal line I'm talking about. So suppose we take that horizontal line from x equal a over here to x equal b over here, and that line's going to lie r units. So the distance from here to here is going to lie r units from the x-axis. Okay? And we're going to revolve the line about the x-axis to generate the cylinder. So basically, I'm going to revolve that line. I really don't need this bottom region here. So basically, I'm going to take that line and I'm going to rotate it all the way around one time around the x-axis. Okay, now let's look at, if you look at a particular cross section when you rotate, like if you were to cut it right here and looked at it from the end, you would actually see a circle. And so now the circle, so what we need to do now is use that circle and find the distance from here, the x-axis, up to the line, and that's going to be the radius that we're looking for. That's going to be that radius that we're talking about. Now, what's interesting here, since this is a horizontal line, the radius is always, all the way from A to B, the radius is never going to change. The radius is always going to be r. So I'm just saying that the radius is r. So the radius is never going to change. So whatever this radius is, it's not going to change as we move across from A to B. So it'll never change. So therefore, in this case, my formula here that I'm going to use is actually just going to be pi times the radius of this circle squared. So all I have to do to find the volume is integrate pi r squared dx from A to B. And so here's A, and then I integrate it all the way over here to B. Now, when we integrate this, since pi is a constant, and actually r squared is actually a constant too, so when we integrate this, we get pi r squared times x. And then if we integrate this from A to B, we actually get b times pi r squared x minus a times pi r squared. We get b times pi r squared minus a times pi r squared. And if you actually factor the pi r squared out, you get b minus a times pi r squared. Now, just remember, b minus a is actually the height. If you look at this as a vertical cylinder, b minus a would actually be the height. So remember that the actual volume of a cylinder is actually pi r squared times its height. And so that's what we got there, pi r squared times b minus a, which is the height. So that jives with what we already knew about the volume of a cylinder. Now in that previous example, the radius that we were revolving actually was constant. But in this next example, the radius is actually going to be changing depending on where we are. So we're going to actually use a function for the radius here. So it says here we want to take the region between the x-axis and the function y equals square root of x. So here's the x-axis, and here's the function y equals square root of x, and we're going to revolve this around the x-axis. So when we revolve it, if we looked at what we would get like a circle here. If we looked at it from the end view, we would actually see a circle. Okay, so what we're going to do now is we're going to get the radius, and so the radius of that circle down there would actually just be the distance from here up to here, and that distance we know is represented by this function. So y equal square root of x. So that's actually our radius. Okay, and then all we have to do now, and remember, let's see, we're going from x equals 0 to x equals 5. So we're actually going all the way out here to 5. So we would go out to 5. And so we're going to integrate on the x-axis from 0 to 5. And then remember, the area is going to be pi r squared. And remember, the r was square root of x. So we get pi times the square root of x squared. So that just gives us pi x. And I can pull the pi outside of the integral. So all I have to do now is just evaluate this integral. And when you evaluate x, you get x squared over 2. And then, of course, we have it times pi. So when we put 5 in, we're going to get 25 halves pi. And then when we put 0 in, we're just going to get 0. So 25 halves pi minus 0 is simply 25 halves pi. Sorry about that. Okay, so we just get 25 halves pi for the volume in this example. Now, we could actually take a semicircle like this and revolve it around the x-axis, just revolve it around the x-axis, and we could use that to get the formula for the volume of a sphere. So let's say we do a semicircle from minus a to a, and revolve that around the x-axis. Well, the radius is actually basically, like we had before, the formula of this circle. And I'll leave you to show this, but you can show that the formula for this semicircle here is actually the square root of a squared minus x squared. And it's kind of like I did on an earlier example, but this time instead of 9, we have a squared. Instead of 3 squared, we have a squared. Okay, so now, so that's our radius. So our radius of our circle, the radius of our circle from here to here, is simply this distance here, square root of a squared minus x squared. Okay, now I can actually use symmetry, so instead of integrating from minus a to a, I could do that. Let's just integrate from here, from 0 over to here, where a is. So we'll just integrate from 0 to a. Now that will only give me half of the volume. So to get the whole volume, I'm going to have to multiply that by 2. That way I have both halves of the sphere. Okay, now remember when we put it in this formula, we do pi times this radius squared. Well, when we square this radical, it'll just eliminate it. So I'll have a squared minus x squared. And then I move the 2 pi out here out of my way. And then when I integrate a squared, that's a constant, so I'll just get a squared x. And then when you integrate x squared, you get x cubed over 3. And then if we evaluate this at a, we'll actually get a squared times a, which is a cubed, minus a cubed over 3. So we'll get a cubed minus a cubed over 3. And then when we evaluate it at 0, we'll get 0 for both terms, so we'll just be subtracting 0. And so what we've got here, this is a cubed. This is 1a cubed, right? So it's 1a cubed minus 1/3 a cubed. So that would leave me with 2/3 a cubed. See, so there's 2/3 a cubed right there. But then I got to multiply it by 2 pi. So when I multiply it by 2 pi, I actually get 4 pi a cubed over 3. Now, if you'll remember, the volume of a sphere is 4 pi times the radius cubed divided by 3. And in our example, the a actually represents the radius. That's the actual distance from the center out to the edge here is A units. So that's the same as R in the radius formula. Now it gets a little trickier when you're rotating about other lines. Like for instance here it says find the volume of the solid generated by revolving the region y equals square root of x from y equal 1 and x equal 4 about the line y equal 1. So here we go, y equals square root of x. Here's y equals square root of x. Okay, and so we have y equal 1 right here. So this is y equal 1, and x equal 4 would be right here. So if we were revolving this around the x-axis, then the radius from here to here would be square root of x. But we're actually revolving around y equal 1, so the radius, we have to take 1 away from that. So if we take 1 away from that, we get the radius is square root of x minus 1. So that's our radius. And now we're actually gonna go, this would actually go from x equals 0. I don't know if I said that, but I should have said x equals 0. So we're going to go from x equals 0 out to x equals 4, and then we're going to revolve this around the line y equal 1. And so we know that the radius between the line y equal 1 and the graph is actually square root of x minus 1. So when we put it in our integral, we get pi times that radius squared. And then if you square that, you get x minus 2 times the square root of x plus 1. And then you integrate that from 0 to 4. And I just moved the pi on the outside. So I didn't actually evaluate this, but you can evaluate it, and you should get that the volume is actually pi times 7/6, or 7 pi over 6. So anyway, that's what happens when you revolve about the line y equal 1. And I believe this right here, I meant to have this say x equals 0. So that's where the mess up was there. Okay, what about rotating about the y-axis? Okay, well, if I want to rotate about the y-axis, I need the radius as a function of y. So I'm going to take this function x equal y squared here, and y equals square root of x. So I'm going to take the y equals square root of x, which is this function, and then I'm going to rotate it around the y-axis. So I need this radius right here. Well, that radius, since I know I can rewrite that as x equal y squared, then I can use my radius and say my radius is simply y squared. And it says in the problem, if you read the problem, you're actually doing this from y equals 0 up to y equal 5. So let's see. It says x equals 0 to x equal 5. But if x is 5, remember, y equals square root of x. So if x is 5, then y would be square root of 5. So actually I'm integrating from y equals 0 up to y equals square root of 5. And so when we integrate from y equals 0 to square root of 5, we get that. And then remember, the radius was y squared. So if we do pi r squared, we get pi times y squared squared. And then I pulled the pi out here. And then you just have to integrate this integral. And again, I'll leave it to you to show that the actual volume that you get by integrating that integral is 5 pi times the square root of 5. And down here's a practice problem. If you want to do a practice problem, you can pause the video and try to work that practice problem. And I gave you the actual formula and the answer there as well. Okay, I don't really have time to cover this last one here, so I'm just going to leave it for you to read. So I've got it worked out for you, so just read this and pause the video if you want to, and my notes are there so you can see my drawing, you can see how I did the math, and hopefully you'll be able to figure out how I achieved the answer that I got here. But this is for revolving about a vertical axis. That's not the y-axis. Okay, so I'm going to look at another technique in the next video for this section.